There we go. Now let me share my iPad. Oh, there we go. Okay, hello iPad, how are you? All right, so last time, for the last, I guess like the last week, we had been working through an example of how you can take a system and write down a simple model of how you understand each of the components of that system behaves on a microscopic level. And then by applying statistics in order to predict what the average or probabilistic behavior of a collection of those stochastic objects, the way that will behave on average or probabilistically, you can extract a macroscopic deterministic understanding of how the system works. Okay, so that's what we did. So I don't want to belabor the point anymore. So let's move on. All right, so now what we're going to do is try to essentially generalize these ideas so that we can apply it to more general problems as opposed to just random walkers diffusing in a solution, and understand essentially what the really basic and fundamental rules are for how you're supposed to do this and treat such systems. All right, so we are going to be doing today what is referred to as equilibrium statistical mechanics. Okay, so in other words, we're going to start talking about what it is that you signed up to take this class for. All right, so now, what do I mean by equilibrium? So equilibrium generally indicates that whatever system you are looking at, you have given it sufficient time in order to settle down into some steady state. And so generally what that means is with equilibrium statistical mechanics, we are for the most part not going to be looking at temporal behavior of a system. That is, it's going to be the behavior of the system after any sort of temporal transients have already died out. Okay. All right, so now the system we're going to start thinking about in excruciating detail is going to be a dilute. That is not many atoms or molecules that we're talking about, weakly interacting. So what that means is that each of the atoms and molecules that we are talking about don't really interact with one another very strongly. And because of that, in general, it forms a gas. So a gas is simply a collection of atoms or molecules that, because they don't interact with each other too strongly, they just kind of bounce around, more or less ignoring one another. And that is what makes them act like a gas. Okay, so what we're going to do is we're going to start with a box. And we're going to say that this box has volume, which we are going to call, logically enough, V. And inside this box, we are going to place a few gas molecules. Okay, and so for the time being, just to keep things simple, what we're going to do is, if we zoom in on each one of these little gas molecules, we're going to assume that essentially all it is just a ball. That is, it's a spherically symmetric ball. It has mass m and some velocity v, and it behaves according to Newtonian mechanics. That is, momentum's conserved, the force applied is equal to the time rate of change of the momentum. So all the good things that Sir Isaac Newton told us about, we will assume apply to these little balls. Now, as we go, as you know at this point, Newton wasn't entirely correct about a lot of things. So when you get on the scale of things like atoms and molecules that make up a gas, sometimes you have to worry about quantum mechanical effects. And so that's going to come later. So we will do that, but that will be several weeks into the quarter. So we're going to start off seeing how a Newtonian weakly interacting gas behaves. And then once we understand that and the language and mechanics of how we handle that, then we'll start introducing more complicated quantum mechanical effects. All right, so that's what we got. We got a box of volume V. We're going to throw into that box a bunch of little balls that are going to bounce around inside that box. And in particular, we are going to add, I guess I should do the same color, in atoms or molecules of this gas. Okay, so those little blue balls, there are N of them. And in general, because we're talking about a macroscopic box, N is going to be very, very, very big, okay? All right, so now what we are going to try to do is, again, we're going to think of these little balls as Newtonian objects that obey Newtonian mechanics, okay? And so in principle, we know how each one of these little balls behave. That is, we look at an individual ball, we know what its position and its velocity, and therefore its momenta are. And so at some initial time, and in principle, we can apply Newtonian mechanics to this, okay, over some time step delta t, and that should allow us to predict what's going to happen to each one of these balls at some later time. All right, trivial, right? All right, but now, as we have discussed, there's a problem with this, okay? And the problem is that there is what is scientifically referred to as a buttload of balls, okay? So we got a ton of balls. All right. Okay, so now, can we do this is the first question. So if we have all these balls, we know their positions, we know their momenta, can we apply Newtonian mechanics in order to predict how the thing is going to behave? And in principle, yes, you can do this. All right. So now what I'm going to do is to define some variables. All right. So first of all, I'm going to define what are called generalized coordinates for each one of the little balls. Okay, so if you're measuring these in a Cartesian coordinate system, then this x here would just be, you know, x, y, and z position of the balls. But you don't have to do that. You can set up any coordinate system that you want, and as long as what you measure is consistent with that coordinate system, then you're fine. Okay, so that's what I mean by generalized, that it doesn't have to be Cartesian. It can be whatever coordinate system that you want. All right, so I'm going to define a variable called big fancy Q, which I will write like this, okay? And big fancy Q is simply going to be the generalized coordinates of every single atom or molecule in my box, okay? So for example, if I have N atoms in my box, then this big Q is just going to be the collection of, in Cartesian coordinates, it would be x1, y1, z1, x2, y2, z2, so on and so forth, up to xn, yn, zn. So it's just the coordinates, spatial coordinates of every atom in the box. Okay, so now, again, you don't have to work in Cartesian coordinates. And so in general, spatial coordinates I'm going to call Q. Okay, so in general, I would write that's why I wrote it as the big fancy Q, because the big fancy Q is the collection of all the smaller individual Qs. So this would be like Q1, Q2, yada, 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 up to Qn, okay? All right, so that's the positions of every molecule in the box. Now, the only other thing we need are their momenta. So I'm going to define a big fancy P, which I write like this. And the big fancy P is just going to be the collection of the components of the momenta. Again, the components in the same generalized coordinate system that you use to define their positions. So this is going to be P1, P2, yada, 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 up to Pn, okay? All right, so now the question is, if I know the positions and momenta of every single atom in the box, can I apply Newtonian mechanics to figure out what's going to happen? And in principle, yes, you can. All right, so in principle, if you know the momenta, Okay, and you look at the time derivative of the momenta, which I will indicate by big fancy P dot. So in general, this dot notation, in case you're not familiar with it, that indicates a derivative with respect to time, like so. All right, so in principle, if I have this vector of momenta of every one of my atoms, okay, and I take the time derivative of that, that should tell me something about the forces that are acting on each one of these atoms, or vice versa. If I know the forces that are acting, that tells me the time derivative of the momenta. And in general, these forces are going to be a function of position, right? So if they, for example, if they hit the walls of the box, then there's going to be a force from the ball on the wall and the wall back on the ball that's going to cause them to rebound. All right. So in general, the forces are going to be functions of the positions. Okay. So this is just Newton's law. So Newton's second law. All right. So Newton's second law says if you know the forces, you can get the time derivative of the momentum or vice versa. Okay. Then once you have the time derivative of the momentum, then that is related to their position, right? So the time derivative of the positions, that's just the speed or the velocity. Okay, so that's simply equal to the momenta divided by the mass. All right, so in other words, you would use Newton's second law in order to determine what P dot is. You can then integrate P dot to get P. And then once you know P, you can plug that in here and integrate Q dot to get the Q's, that is the positions. So you're just doing Newtonian mechanics. All right, so, all right, we're done, right? Piece of cake. All right, so now the problem with this is that N, our number of balls, is extremely large. Okay, again, for macroscopic systems, we're talking about on the order of Avogadro's number, which is 6 times 10 to the 23rd atoms or molecules. That's a lot, okay? And it turns out this number is so big, it makes this job impossible. All right, so now let me show you that it's impossible. All right, so let's work through an example. All right, so now I add, what is the fastest computer that you can find these days? All right, so now it turns out that the fastest clock speed for a processor that you can go out and buy is on the order of about 8.5 gigahertz. So I went and looked this up not too long ago. All right, so the fastest possible clock speed you can get your hands on for a computer processor is about 8.5 gigahertz. Okay, so what does that mean? So what that tells you is essentially how many computational operations it can perform per second, right? So in other words, this is telling you how fast the processor can go. So what this tells you is that the time per operation is just 1 over the clock speed. Okay, so if we find out how many operations we need to do, we would then just divide that by the clock speed in order to give us how long it will take in order to perform that calculation. All right, make sense? Very good. So now the question is, so let's say we have, let's say N is on the order of 10 to the 26. All right, so it's like a cubic meter of gas. All right. Okay. And so the question is, if we have 10 to the 26 atoms, all right, so what we would do is we would write down Newton's equations, which are differential equations, right? They're differential equations because they're time derivatives. And then what you would do would be to numerically step through this differential equation one time step at a time, right? So you plug in the initial conditions, you'd say, okay, let me run for one time step delta t, and what are the positions and momenta going to be after that time step? So my question is, how long is it going to take you to do just one time step? So how long to update your Q's and P's for just one time step? Okay.
It's like 10 to the 17 seconds, right?
We're gonna work through it in excruciating detail, but it's big. Um, yeah, you're close. All right. So again, for each particle, we need to know its position. So that's 3 parameters. We need to know, say, x1, y1, z1. So that's its position. We also need to know its momenta. So that's px1, py1, pz1. All right, and remember, we're assuming that these atoms are as simple as they could possibly be, that is, spheres. All right, so things which are actually molecules that have some shape to them, it's going to be even more complicated than this because you have to keep track of Eulerian angles and so on and so forth in order to determine their orientation. So this is as good as it gets, okay? All right, so what this means is that every atom requires 6 parameters in order to describe it. Its positions and its position and momentum. All right, so now what we're going to assume is that, so what we're going to have is, we're going to be, say, given some initial conditions. So we're going to know, for example, what its position is at some time x, let's call it xt. Okay? And we want to know what is its position going to be at xt plus 1. That is 1 time step. Okay, and so what you do is you take your initial position, you perform some computational rule, specifically Newton's equations, okay, and this, whatever the result of this rule is, that allows you to update the positions in order to get what the new position is. All right, so in other words, what we're going to do is say we start with x1 at time t. Okay, then we perform just say 1 computation, which again, in practice, this is not what would happen because you'd actually have to perform several computations for each parameter at each time step. But let's say that we just perform 1 computation, and that allows us to update what it's going to be at time t plus 1. All right, so this is 1 computation. And similarly for the other coordinates and the other momenta. Okay, so in other words, for 1 particle and 1 time step, we at minimum have to do 6 computations. And again, this is an optimistic estimate. All right, so in other words, if we got 10 to the 26 atoms, the total number of computations we have to do is 6 times 10 to the 26. That is pants crappingly large, yes? That's a big number. All right, so that's the number of computations we have to do for 1 time step. And then what we want to get is the amount of time this takes. So time for 1 step. Okay, and so as we just described, what you would do would be to take this number of computations you need to perform and then divide by the clock speed. All right, and what you get is something on the order of 10 to the 14 seconds. Okay, 10 to the 14 seconds. How, okay, what is that? Okay, so now what you need to know is that in 1 year, there are how many? 3 times 10 to the 7 seconds in 1 year. All right, so how long is it going to take? So we have 10 to the 14 seconds, and then we just convert that to years. So that's divide by 3 times 10 to the 7 seconds, 1 year. So we get that 1 time step will take on the order, give or take, 10 million years. Piece of cake. All right, so if this is what you're going to do to get your PhD, you better get started, right? So this is completely impossible, right? That's just to do 1 time step. And then we want, you know, that's what, like a nano or a femtosecond in the actual container. So, I mean, in order to get any kind of macroscopic behavior, you'd have to do this billions of times. So now you're talking like 10 to the 15 years. This is longer than the age of the universe. You can't do it. It's impossible. Okay, so sad face, wah, wah, wah. No go. All right, so how are we going to do it? Well, what we're going to do instead is statistical mechanics. All right, and so what statistical mechanics, the basic assumption of statistical mechanics is that you don't need to know the positions and momenta of every single atom in the container. All you need to know is some macroscopic quantity which describes the average of all of the behavior of all the atoms and molecules in the container. Specifically, a function that we are going to be continuously interested in is the energy. Okay, so let's look, and the reason for this is typically energy is conserved, right? So what's going to happen is instead of having to keep track of 10 to the 6 times 10 to the 22nd numbers, okay, so we've got all these different coordinates up to xn, yn, zn. Okay, so this way you have to keep track of 6 times 10 to the 26 numbers. No, 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 not in my house, no. Okay, so the way we're actually going to do it is just keep track of one number. All right, and the one number we're going to keep track of is the energy. Okay, now the energy is, so now the trick here is that the energy is a function of each of these numbers. So it's a function of the x1, y1, whoops, this is supposed to be a 1, z1, so on and so forth, up to xn. Okay, so it is a function of all these numbers, but it turns out in order to calculate things like average energies and so forth, you don't have to keep track of every single one of these numbers. You can just look at like their average behavior and the deviations from that average behavior and so forth. So instead of 6 times 10 to the 26 numbers, you just keep track of one number, the energy. Okay? All right, and in particular, once we're able to write down the energy of our system, we are going to assume that the probability to find the system in a given state is a function of that energy. Okay, so the problem is a function of energy. Okay, so in other words, what we're gonna, our goal here is to write down some probability distribution function. And that probability distribution function is going to be a function of the energies of whatever states it is of our system that are available to it. And the probability to find it in any of those states depends upon what the energy of those states is. Okay, so in other words, once we find the energies, we know everything. All right, so let's do it. All right. And so now, when we start out doing this, we're going to start out with the simplest possible scenario, okay? And that is, so let's say that we have, again, our box, okay? And our box has atoms and molecules in it. Okay? And what we are going to assume is that this box is completely isolated from the outside. So anything we care about, we only care about what's happening inside the box. We don't care anything about the outside because the inside and the outside can't talk to one another. All right? So now, so what that means is that no energy can flow into or out of the system. All right? So specific, so the walls here are made out of some advanced unobtainium, or whatever the hell you want to call it, such that the inside of the box is completely isolated from the outside. And so in other words, any energy cannot get in and no energy can get out, whatever kind of energy you're talking about. Okay, so in other words, the energy of the system our system is a fixed constant. The energy does not change. Okay? And so now what we're going to imagine is, instead of just one box, imagine you have a whole array of these boxes, each of which can be in some state, whatever that means, whatever we mean by state. We'll talk about that in a second. Okay, but now, so each of these boxes can be in a different possible state. And what we want to know is, for a given total energy, how many possible states are there that this box can be in? Okay, so for a given fixed constant energy, how many different states are there? All right, so that's what we want to answer. All right, so now this idea that we are going to look at all the possible available states to a system that is at a fixed constant energy is what's referred to as the microcanonical ensemble. Okay, so it's called an ensemble because we're imagining a whole collection of these different boxes of gas, and we want to look at all the, in other words, the number of boxes we're going to have is the same as the number of possible states. And the microcanonical here indicates that we're looking at fixed energy. Okay, so whenever you hear microcanonical, you should think fixed energy.
Quick question.
Yes, please.
Are all these energy states equally likely, or are some preferred over
Yes,
others?
that is the assumption we are going to make. We are going to find out the number of states available to us. And because they are all at the same energy, that means that they are all, because of this assumption we made right here, that means that they are all going to be equally likely. Yes, that's exactly correct.
Okay, thank you.
Okay. All right, so let's get some experience talking about this problem using a physicist's best friend. And that is, so let's work through an example here. Physicist's best friend is the harmonic oscillator. Right? So I mean, if your goal in life is to become a quantum field theorist, you know, what a quantum field theory is, if you sit there in your chair and you think, what if everything in the universe was a harmonic oscillator, right? Physicists freaking love harmonic oscillators. So let's talk about a harmonic oscillator. Okay, so an example of a harmonic oscillator is, for example, a mass attached to a string, okay, which is attached to the wall. And this thing slides on a frictionless surface. Okay, so this thing just oscillates back and forth forever. Okay? Now, in order to, so now what we're interested in is the energy of our harmonic oscillator. All right, so now you guys know the energy is just the kinetic plus the potential. And the kinetic energy is just p squared over 2m, right? And the potential energy for a harmonic oscillator is 1/2 kx squared. Right? That's a harmonic potential. That's what makes it a mechanic or a harmonic oscillator. Okay, so now again, this is again assuming it, oh, somebody's saying something. What are we saying? Chat. 5, that's right, exactly. Bigger than a forehead. Oh, somebody had, oh crap, I lost. If you have a question, please say it, because you know I got math running through my brain. I'm looking at my iPad. It's hard for me to keep track of what people are typing. There's only 10 of you, so if you got a question, just ask me, okay? All right, so this is the energy of a harmonic oscillator. And again, this is in Cartesian one-dimensional coordinates. So in generalized coordinates, I would write this like this. So it's essentially exactly the same thing. It's just k, oh crap, plus kq squared over 2. All right, so that's generalized coordinates for a harmonic oscillator. All right, and so what this harmonic potential is telling you is that if I were to plot position and potential energy, what this function is a, you guys know all this, it's a parabola. Okay, and the way that this harmonic oscillator behaves is exactly like if you had a container with a parabolic shape and you put a mass into it, and what it does is it starts rolling back and forth on the surface forever and ever. All right, and so now, for example, when it reaches its highest possible point in this potential, it has, you know, whatever this Q max is, and that also corresponds to 0 momentum. All right. Then when it gets down here to the very bottom of the container, it has position of 0 and it has some maximum momentum. All right. So in other words, once I specify the position and the momentum, that tells me what the energy is. All right. So now the collections of all possible P's and Q's that yield the same energy, that's what I mean by the collection of states that give you a given energy. Okay. All right. So now let's think about this. All right. So now, you know, we're upper level physicists now at this point. So we don't want to call it the energy of the system. We're going to call it the Hamiltonian of the system. Okay. So the Hamiltonian, whoops. The Hamiltonian for a simple harmonic oscillator is just this. Okay, so now what I'm interested in are all, so again, let's assume I have a fixed, constant energy, which I'm going to call E naught. Okay, and so now what I'm interested in are all the possible combinations of P and Q that will give me this fixed constant energy E naught. So in other words, I'm interested in the P's and Q's, P naught and Q naught, K Q naught squared over 2, that give me this fixed energy E naught. Okay, now, just to make the discussion simpler, I am going to redefine my momenta and my coordinate. Okay, so instead of calling it P squared over 2m, I'm just going to say that this whole thing here, this is my momentum, P naught, okay? And this is my position, because these other things are just constants. Who cares about constants, right? So I'm just going to absorb those constants into my definition of these coordinates. So in other words, I'm going to define this to be P naught squared plus Q naught squared. Okay, so what is this? This is the equation of a circle, yes? So what I have here is, so if I draw a coordinate system, okay, so let's say this coordinate here is my Q, and this coordinate here is my P. And what I'm interested in is all the combinations of P and Q that give me some constant E naught, right? And so the E naught is serving like a radius. So it's just a constant distance in this coordinate system. And I want all possible combinations of P and Q that give me that E naught. And so what this is a circle. Okay. And again, if I hadn't absorbed these constants into P and Q, so then it would just be an ellipse instead of a circle. But who cares about ellipses? It's a circle, for God's sakes. So let's talk about circles. Okay, so now every point on this circle. So again, the radius of this circle is equal to the square root of E naught. So in other words, as long as we are on this circle, we have energy equal to E naught. Make sense? So in other words, every possible point on this circle corresponds to one state of our harmonic oscillator that has energy of E naught. Okie dokie? Okie dokie. So this plot of, so now this plot here, this is not actual real physical space, right? Because the axis, one of the axes here is momentum. That's not real physical space. So this kind of plot where you plot the momenta and the spatial coordinates, this is what's referred to as the phase space. Okay, so this is the phase space plot of a harmonic oscillator with constant energy E naught. Okay, so now what if, so now again, we're gonna only be talking about systems of constant energy, but what if we change the energy? What would it look like? Okay, so let's draw, let's draw, shall we? So what I'm gonna draw is this. Okay, so on this axis, I'm gonna put the momentum. On this axis, I'm gonna put the position. And on this axis, I'm going to put energy. All right. So in other words, this point right here is where we have zero momentum and zero spatial coordinate. So in other words, at this point, the thing is not moving. And now what we want to see is as we change P and Q, that is, as we move along in the horizontal plane, what does that look like? Okay. So now if we go back to our Hamiltonian here, we can see the energy is quadratic in both the momentum and the position. So in other words, if I were to say, just look at the energy as a function of position. So here, let me do the, watch this. Oh, I'm going to do my position in purple and my momentum in, not pink, red. Okay, so in other words, the energy as a function of position is, as we described previously, this is a parabola. So in the EQ plane, it is a parabola. And similarly, in the in the EP plane, it is also a parabola. Okay, so let's see if I can draw this like so. And so in other words, what we're doing when we look at a specific energy is we're taking a two-dimensional cross-section through this paraboloid, is what it's called. All right, so when we pick a given energy, what we're going to do is, let's do black. So what we do is at a given energy, we pick a given energy. What that is going to give us is essentially we're taking a cross-section of this surface. Okay, and it's this circular cross-section of this paraboloid that when we look at it in two-dimensional space, that's what this circle is. So in other words, as we increase the energy, okay, so if we were to increase the energy, what would happen would be that we would come out here or come to some higher point, and that would give us another circle of larger radius, right? Can you see it? Is it like you're there? So again, this would be where the virtual reality would come in handy. I could draw all this and then we could spin it around and what, but you know, what can you do? Okay, so in other words, this circular cross section of this paraboloid is when you're taking a constant E naught, and when you take a constant E naught through that paraboloid, that gives you this circle. Okay. All right, so now let's go back to our original question here. Where's our original question? Okay, so our original question is right here. Let me draw a big red box around it. So if the energy of our system is a fixed constant, how many different states will that correspond to? Okay, that's the question. All right, so now what that means mathematically is, again, if we come down here to this circle, what I'm asking is essentially how many points are on this circle? That's the kind of thing that will give you a headache if you think about it too much. Okay, so what does that mean? All right, so what we got to do is agree upon a way, essentially, to count the number of states that are on this circle. Okay, so let's again look at our P and Q, our phase space here. So again, this is P and this is Q. All right, and so now what I'm going to do is I'm going to look at a point. Say, what the? So here's my point. I'm going to say this is at P naught. Well, that's backwards, isn't it? It's at Q naught, P naught. And I'm going to say, okay, if the system is at Q naught, P naught, that is one state. All right, but I can't just say that that point is the state, or else I'm going to, you know, how are you going to do this? So what I'm going to say is that if I am at a given point, and then I go an infinitesimal distance away in the Q axis. So in other words, I go to this point here, which is Q plus, or Q naught plus dQ. And I go this direction. So I go to P naught plus dP. That if I am somewhere within that infinitesimal range around this point, I am in the same state. Okay, so in other words, what I'm doing is I'm defining little boxes. Okay, little boxes of width and length dq and dp, and I'm going to say everything that falls within that box is one state. Does that make sense? Okay, so in other words, if the area of this box is one state. Make sense? Now, this I just have one p and one q. But if this were like a, you know, whatever, an 8-dimensional harmonic oscillator or whatever, then I'm going to have more coordinates than this. So in general, instead of area, generally speaking, what I'm talking about here is volume. Okay, so the volume of this box is one state. Okay, but now we have another. So now we've agreed on what we mean by one state. We mean the volume in a infinitesimally wide box of phase space. Now we have another problem. So that's solved one problem. What is a state? Now we have another problem. Okay, so here's the problem now. So this is our phase space for a harmonic oscillator. And I told you that what we're looking at is a circle. And any point on this circle corresponds to a state. Not now. Okay, so I look at a point on this circle. What is the volume of that point? Or what is the volume of that line? 0. Points and lines don't have volume, right? Okay, so now we got a new problem, is we want to calculate the volume of a line. You can't do that. Okay? So what we're going to do is, again, this circle has radius equal to the square root of the energy. Or in other words, let's not make it too complicated. So the radius depends upon the energy, E naught. Now what I'm going to do is say, what if I look at that energy and I increase the energy by a little bit? Okay, so now what I'm going to do is to look at another circle. Okay, and this circle has radius equal to the original energy plus some infinitesimal amount, delta E. Now, okay, now, so what I have now is an annulus, right? And so now I can calculate the volume of this annulus. All right, so in order to count the number of available states, what I'm going to do is to calculate the volume of this annulus, and then let delta E go to 0. So in other words, I'm looking at a specific energy, I let it get a little bit bigger and calculate the volume of that, and then I shrink it back down to where it originally was. And it's just a math trick that allows me to do this. Okay? Okay, so. All right, so what I want to do is to look at, I want to count the number of states within an annulus of width delta E, and then let delta E go to 0. Then let delta E go to 0. Okay, so I'm going to define a quantity. I'm going to call this quantity capital omega, that is a function of energy. And let's say I multiply this by this infinitesimal width. So this is equal to, so this is the number of states in region of width delta E. Okay, so this is my definition of this quantity omega. Okay, so omega times delta E is the number of states within this thing. Okay, so now how can I calculate this? All right, so again, what I have is a bunch of little boxes, each of width dq and dp. And so now essentially what I need to do is just add all those up. Okay, so the total number of states is just equal to, if I take, you know, the volume of each one of these little boxes. So the volume is just the height times the width, right? And then I just add up. I do an infinite sum over all my little boxes. Well, what is that? That is an integral, yes? So I integrate dp dq. And I'm integrating for all values of the energy between E naught and then of my Hamiltonian. So, okay, so I'm integrating essentially my Hamiltonian between all energies E naught and E naught plus delta E. Okay. And so, in other words, this omega of E, this is like it's what's referred to as like a density of states, right? Okay, and so the density of states is equal to 1 over delta E integral over the region of interest dp dq. Okay. All right, so now, so what I'm doing is I have, well, I used different colors earlier. So what I have is this shape that I drew like this. And what I'm doing is I'm taking this shape and dividing it up. I'm essentially counting how many boxes okay, so if I zoom in on this box has height dp and width dq. And so what this integral is telling me is simply the number of boxes in this shape. Okay? And again, as somebody pointed out previously, what we're doing is we're assuming that everyone, because they all have the same energy, okay, we're assuming that to be in each one of these states is equally probable. Okay, so in other words, this is also my probability density function. And what I mean by that is, let's say I have some function, O, whatever it is, and I want to calculate the average value of that. Then what I would calculate would be this, essentially. Okay. All right, so this is an introduction to how we are going to start computing quantities of interest in the microcanonical ensemble within equilibrium statistical mechanics. Wow, so many big words. I feel so smart saying such a thing. Okay, and so again, what's happening here is that this, so again, what I'm doing, the function that I'm taking the average of, that's there. This dp/dq, this is essentially the probability density function, and then I add them all up. And the fact that I add them all up in the same way means that each little box that I'm adding has equal probability. That is, I don't have to weight one box differently than another. Okay, so I think that's probably where we're going to stop today. So does anybody have any questions at this point? All right, cool. Then we shall return to this on Wednesday and start doing some more interesting calculations. Okay? All right, so until then, I will see you later.